In this lecture, we will combine the first and the second laws of thermodynamics to come up with the most important equation in chemical thermodynamics. We start with the definition of the Gibbs free energy, which is given by enthalpy minus the temperature multiplied by the entropy. If I differentiate both sides, I get this equation. And now remember that the enthalpy is equal to the internal energy plus the product of the pressure and the volume, and the other terms remain as they are. If I expand this, I get a differential change in the internal energy plus pressure times the differential change in volume plus volume times the differential change in pressure, and the remaining two terms are as they are. To describe the change in internal energy, we will use the first law. Now, the first law says that the change in internal energy is the amount of heat plus the amount of work entering the system, and the amount of heat entering the system is equal to temperature times the change in entropy. We can write it in this manner because internal energy is a state variable, so we can consider this process to be reversible without losing any information. And we can also write work as minus P dV. So here we have a closed system and we only have expansion work. Now, if I substitute this equation here, I get this TdS minus PdV plus PdV plus VTP minus temperature times change in entropy minus entropy times change in temperature. And now some terms just fall off. So the TdS terms fall off and the PdV terms fall off. So all we are left with now is dG equals VdP minus S dt. Now this is a very important equation because it tells us how the Gibbs free energy varies with pressure and with temperature. Yes, let's go a bit further and start from this equation to see how the Gibbs free energy varies with pressure and temperature when the other variable does not change. Now, let us say the temperature is constant, so this term will fall off, and then you can say that the variation of Gibbs free energy with respect to pressure at constant temperature is simply given by the volume. And if I divide both sides by the number of moles, I can write this as the variation in the molar Gibbs free energy with respect to pressure at constant temperature is equal to the molar volume. Or at constant temperature, we can write this equation in this way. I'm sorry, this should be pressure. Now, if you look at the slide in the presentation, it shows you how the molar Gibbs free energy varies with pressure. Now, the molar volume of a material is typically very high for a gas compared to the liquid and the solid form. So, for example, if you have 1 mole of water, that's 18 grams of water, about 18 milliliter of water, that's a very, very small volume, 10 to the power minus 6 metric cube. If the same mole of water evaporates and becomes water vapor, it will occupy about 22 liters. So, the molar volume of the gas is much higher than the molar volume of the liquid. And the slope of these lines reflects the molar volume. For example, the slope of the red line is the molar volume of the gas as the pressure is changed. You will also note here that for the solid and the liquid, the slope is constant. So, typically the volume of a liquid will not change as you increase the pressure, not by a lot. So, this also tells us how the phase will change with respect to pressure. So, here at very low pressures, we have a gas. So the Gibbs free energy is minimum for the gas in this region. Now, as we increase the pressure, as we go up to this point, now the liquid has a lower lower molar Gibbs energy compared to the gas. So where did the pointer go? So this is now the stable phase under these pressures, and as I keep increasing the pressures, I finally enter the solid phase. At very high pressures, the solid has a lower molar Gibbs free energy, or not free energy, lower molar Gibbs energy compared to the liquid. So this tells you how the Gibbs free energy varies with pressure, and we are going to see more of this equation in a little bit. So let's derive that for an ideal gas. If I try to integrate this equation, I can write it in the following way: from initial pressure to final pressure, volume dP, and I can convert this to the molar form if I divide by the number of moles on each side. The left hand side simply becomes Gibbs free energy at the final pressure minus the Gibbs free energy at the initial pressure, and the right hand side, the molar volume is given by the gas constant multiplied by the temperature divided by the pressure in this form, and this is equal to RT log of the final pressure divided by the initial pressure, and I forgot M here, and therefore the molar Gibbs free energy at any pressure can be described with respect to the molar Gibbs free energy at some other pressure plus the gas constant multiplied by the temperature multiplied by the natural logarithm of the ratio of the two pressures. Now this equation is true at constant temperature because we pull the temperature out, so it's true for an isothermal process, and it's also for an ideal gas. But it turns out that the equation is very similar even for liquids, as we will see later in some other lectures. Okay, so this is how the molar Gibbs free energy, molar Gibbs energy changes with pressure. What about temperature? So this was the fundamental equation of chemical thermodynamics, and at constant pressure this term will fall off, and then we will have this equation. So I have divided both sides by the number of moles to convert Gibbs energy to molar Gibbs energy and entropy to molar entropy, or we can write this as now. Let's plot this one graphically as well. So this is figure 3.3 from Atkins. Now you notice that the slopes in this line, on these lines, are negative. However, the slopes in these lines were positive because molar volume is a positive quantity. Entropy is also a positive quantity, therefore minus of entropy is a negative quantity. So the slope of G versus T, which is given on these curves, must be negative. Again, the molar entropy of the gases are much higher than those of liquids and solids, so this line has a much higher slope. And this figure also tells us why things melt and eventually boil as we increase temperature. So at very low temperatures, most materials are solids, and as you raise temperature, the molar Gibbs energy of the liquid becomes higher than that of, becomes lower than that of the solid. So liquid becomes the equilibrium phase between the melting temperature or the fusion temperature denoted by Tf and the boiling temperature. As you increase the temperature until it reaches the boiling point, the Gibbs energy of the gas becomes smaller than that of the liquid, and therefore the material evaporates. So this is the equation, fundamental equation of chemical thermodynamics, and we will deal with this a little more when we are discussing mixtures.